Good afternoon. It is a distinct pleasure to welcome you to this Society Labs webinar about quantum computing. My name is Michiel Borrell, and I will be your master of ceremony. Now, of course, in the invitation, you saw that Julian van der Zwan would be the host today, but I am so passionate about this topic and so excited that we have such a huge audience. We had over 200 registries for this webinar. We now have about 80 something people online. Probably some more people will join just in a few minutes. And I'm quite happy with this this huge interest in this theme of today of quantum computing. As you might know, as CTO of Society, I'm part of the CTIO network of Capgemini, and which brings together about the 8 or 10 CTOs all across our company. And each CTO has a special area of interest, and for me, it's computing futures. And of course, within computing futures, quantum computing takes a very important and promising role. And so today, it's our objective in the next hour or so to inform you about what quantum computing is, to discuss where the opportunities lies, also to discuss a little bit what Capgemini's role and within that Society's role could be in this new area. But also, I have the objective to start a community of people that are interested and passionate about quantum computing so that they can help me drive the vision and drive the strategy for all of the Capgemini group. And so going forward, I intend to have many more webinars and trainings about this theme of quantum computing. Just before we jump in, some household remarks. First, you have to understand that this session will be recorded so that we make it available to everybody that could not join us today in live, that they could always follow up later on and follow it and look at the recording. Secondly, I encourage you to ask questions while we are going through the presentation of Julian, and you can use the Q&A tab within your control panel. If you look at your control panel that came up when you've joined, you also see a specific section of where you can ask questions. And please use that because then I will be able to insert your questions into the conversation that I will have with Julian Von Felse. At the end, when we still have time, we will also open up all microphones so that you can ask your questions directly as well, and maybe share some observations and ideas that could be of interest to everyone. But for now, we will keep the microphones closed and only have the speakers sharing video and sharing sound. And of course, towards the end or just after the webinar, we will share the slides with you that Julian is going to use. So that's for the household remarks. So it's my pleasure to introduce to you Julian Von Felse. So Julian, very welcome to this webinar. Very nice to have you, and great that you are willing and able to share with you some ideas and some information on quantum computing, and I'm looking forward to the discussion. We have been working together for the last, I would say, half year or something, Julian, to get some ideas going on quantum computing, and more importantly, what it means for Capgemini and Society as part of Capgemini. But maybe it's good to introduce yourself a little bit, Julian. So who is Julian Von Felse?
All right, thanks. Thanks for inviting me here. It's great to see that there are so many people showing up. I think it's an exciting topic, so I'm very curious to hear what you guys have been listening to about quantum technology, and I'm happy to have the discussion afterwards as well. So yeah, my name is Julian Von Felse. I work for Capgemini since 2 years now. And well, disclaimer at first, there are so many things I do not understand about quantum technology. It's a fascinating topic, which there are many different parts of, and therefore I'm even more excited that there are so many people on the call, because I think the way we can learn as Capgemini more is together. But that being said, I have some background in computational physics. I did a theoretical physics master at the University of Amsterdam and some research, and mostly researching how can you use computers to simulate systems where you need a lot of resource and a lot of compute power. And I think that's a good starting point for investigating what quantum technology will mean.
And you have been looking at quantum computing for the last couple of years, right?
Yes. So my master's, Capgemini, and now together with you. Yeah.
Okay. So very good, Julian. So welcome again. Maybe before we dive into the first question that I have for you, maybe we should first ask a question from the audience. Throughout the presentation, we are going to use something called Mentimeter. And so if you go on if you take your phone and open up your browser and go to www.menti.com and then use this code 882321, then you will be able to interact through these questions. And the first question is quite a simple question. So what do you believe when you look at what's growing at a faster rate? Is that the total volume of data in the world, or is it the storage capacity of disks? Now, I see that already we are getting the first answers in. So people would have found the site, so it's going quite quickly. So we have now about 20, 22, 23 people that have answered the question, Julian. And as you can see, by far the majority believes that the volume of data in the world is growing faster than the storage capacity of disks. So is that the right answer, or is it the other way? That because nowadays you can buy a terabyte of disk for less than 50 euros. So what do you believe?
Yeah, so I think there is some consensus. Most people seem to think there's more, the volume of data is growing faster, and that's definitely right. But it's interesting to zoom out of that a bit, right? I mean, in my laptop, I have 2 terabytes of storage, and I can store virtually a limitless number of pictures on my computer. A number of years back, that would have been impossible. And actually, the number of volume of data that is really exploding. So it's not just on my computer, but it's also in the cloud. So we can go to the next slide.
Yeah.
We see that.
So that is the question. Why do we need new compute systems, right? That's the question that you're going to address first.
Exactly. So we may know that the number of data is really exploding, which is, I think, a fascinating fact by itself. Actually, in the past years, the number of data, the data volume has doubled in a few years, in 3 years, and it's expected to grow to 275 zettabytes in 2025. So it will be an exploding amount of data, and the storage capacity that we have is not able to cope up with the amount of storage that we need. So maybe less known from the data is also that the number of compute requirements that we use is exploding. So the number of CPU hours, the number of the time that we use our computers to do all kinds of calculations. It seems like with this enormous growth of number of transistors and compute power, that we have virtually limitless amount of data and compute power available. But in reality, we see that for all kinds of big calculations, we need more and more and more compute power. So I think last webinar, you guys spoke about natural language processing and about the BERT model. Is that last webinar?
Yeah, it was 2 weeks ago, NLP, yeah.
Excellent. I thought it was fascinating, by the way. But there was this model called BERT, and it had about 160 billion parameters to be used within this model. So it's an extremely big model that takes a lot of time to compute. And this model is still, much smaller than the number of parameters that we have in our brain. So we can, if we want to grow closer to how we simulate, our brain and how to simulate all the different smart things that we can do, it is expected to be much more compute power.
Yeah. So, but then in the since I think the 60s or something, we have this Moore's law, where the number of transistors on a chip is doubling every 18 months or so, and so this is still kind of exponentially growing, right? Doubling after every 18 months. Why isn't the so is that ending? You say in this slide it's ending, but
Yeah.
so far it's still growing, right? But it's slowing down. That's what you're saying.
Yeah. So the thing what they're doing is just they make more transistors in a smaller space, just packing them up as closely as possible. Well, just naively you would think that there is a limit to it, right? I mean, at some point there's just not more space. So this limit has been approaching for a while now. What you see on the curve on the right is the processor performance of a single core.
Yeah.
So we do all kinds of tricks. We have multiple core, and we do like double patterning and all kinds of different tricks to make sure that we keep on improving, keep on innovating. But at some point, I mean, there's nothing we can do. I mean, at some point, the space is just up, right? We need to come up with different ways.
So we're in this conundrum where the demand is increasing at a accelerating rate, while the growth of the compute power is slowly but surely kind of slowing down, right?
Yeah.
So this gap is starting to occur, and it will only get bigger. Now, of course, then computing, quantum computing is one of the promises is that it would offer, how do you call it, unlimited compute power. Now, before we dive into to see how we can increase the speed of the growth of compute power, maybe we should ask another Menti question. So if everybody can take their phone again. And so the question that we have is really simple. It's a word cloud. And the question is, what would you do if you had unlimited compute power available? So let's dream a little bit. That quantum computing or other technologies are providing it. What would you do actually with that compute power? So let's see what the people are coming up with the idea. Create a second brain, rule the world.
I like that one.
Very interesting. Two very good ones. Find extraterrestrial alien life. Analytics stop working. Drug discovery, put everything into memory, analytics, became a Borg. And that's always great with this group of people of Society Labs, that there is never any limit in their imagination. Break cryptography, predict the lottery numbers. Fantastic, yeah? So, any surprises for you, Julian?
So first of all, there are a lot of interesting things, right? I really liked how people, dreamed on and not just be limited with the things we can do today, but really take it to what is possible in the future. So I think what is interesting is that there's many different kinds of problems behind here. I see optimization problems. I see a lot of AI. I see some quantum chemistry. I see maybe like big number crunching applications. And I think that
it's an interesting one, right?
Yeah. And maybe something is not necessarily compute power, but it's more like robotics or something. If we become a cyborg, I think that would be fascinating. Maybe I can do like have some extra visual lenses in my eyes or something. But I'm not sure if that's compute power or is that like just robotics.
So it's quite interesting. So there's not a lack of ideas of what we could do with unlimited compute power. So let's shift gears a little bit and let's look at some of the approaches that are at this time actually being followed to provide that compute power. So because we can all dream of how we are going to use it, but how is it going to be built?
Yeah. All right. So if we regard from the previous slides that on the one hand we have all these things that we want to build, and we need more compute power and more data to do so. And on the other hand, our current systems are lacking. Well, basically we have to come up with something new, right? Either we have to build the whole world with the old computers, or we have to do it in a smarter way. So if we go to the next slide, I think there's, and that's also our perspective, there are three major categories of compute systems that will be available in the future. And we see there's so many innovations on the different parts. In the past, maybe 10 years or so, GPUs have really been fundamental in accelerating research in artificial intelligence, in training models faster, having deep learning models, all kinds of different kinds of conventional computing that really helped in bringing the next phase of applications. But we can also see different kinds of accelerators, GPU kind of machines. You have tensor processing units. We can do stuff on the clouds. We have high performance computing, which is sometimes more academic. But it's all still conventional computing using traditional architecture and hardware. We also have other types of future of compute, which is called neurons, neuromorphic computing. And different from conventional computing, it's much more focused on how can we mimic our brain in order to make systems that are as intelligent as possible, and also that require much less energy. So we can do some artificial intelligence today already, but for many applications we need, server farms that use as much energy as half a city. Well, on the other hand, our brain use virtually nothing. So how can we mimic our brain and do smarter things? But of course, we are here today not about neuromorphic or qubits, but more about quantum computing. So if you go to the next slide, we can see that even within quantum computing, there already are so many different types of quantum computer. We're really at the early stage where it's not yet set. It's not that there's one quantum computer that will rule the world. It's not that IBM is a winning ticket and their quantum computer will be in all our houses in 5 years.
So there are different strategies for building this quantum computing, right? Quantum computer.
Absolutely, yeah. So that's just within quantum computer. And what I think is fascinating is that it's not just quantum computing that will deliver business value in the future. It's not just quantum computing that will take over computers. It will much more be likely to be a combination of qubits, of bits, and of neurons, of all these different systems, and not just for different use cases, but also working together. So bits that work together with a quantum computer in order to compile systems, to have readout systems, all kinds of middleware, smart systems, a whole combination of these things.
So if I understand it correctly, what you're saying here is that the future, like you said, is heterogenic. So companies don't have to choose whether they choose for bits or for neurons or for qubits. It will be a combination of them all, right?
Absolutely, yeah. So maybe for you as well, Monsieur. So within the CTIO office that you mentioned before, we're now tackling these three domains, right? Why did you, well, before we were focusing more on quantum computing, why did you switch to having a bigger perspective and including neuromorphic and quantum and also conventional computing?
Well, so for Capgemini, obviously, it's very important to look at what kind of clients are already working on this and what kind of clients are really at the bleeding edge of the need for processing power. And then what I've realized is that it's primarily in the area of high performance computing. And so instead of looking specifically at quantum computing as a solution, we should look first at the problem of providing more compute power. And then most of the clients that we talk to, they don't care about the specific of what technology is going to provide it. They want to kind of, how do you call it, hedge their bets, as long as they will get this additional compute power. And then they would bet both on neuromorphic computing, as on quantum, as on bits. So, and this of course was inspired by a talk that I had with the CTO of Airbus, of course before they are in their present existential crisis, but they were looking at it not as a separate thing in isolation, quantum computing, but they said it should be part of a strategy of how to provide the processing power, the compute power for the future. And so that's why I immediately thought, okay, we have to broaden the scope, not only look at quantum computing, but let's look at all the approaches that are going to provide this additional compute power.
Yeah. So, and also the answers that were provided in the previous Menti question, eventually I think those are the questions that we want to tackle. And there are, none of these, all of these use cases are either, I mean, they use a combination of these kinds of architectures. So it would definitely not be that quantum computing will be able to solve all of them.
Okay, so before we switch gears once more, let's ask another Menti question to the audience. And the question is quite straightforward. So what do you think is the most promising next generation compute system? Is it the tensor processing unit? Is it neuromorphic computing, or is it quantum computing? And let's give the audience a little bit of time to answer this question. So it's surprising, or maybe not so, that most people say, by far most people say, that quantum computing is the most promising next generation compute system. And things like a tensor processing unit or neuromorphic computing is a little bit less. Now, I don't know if it gets less press or there's less hype. Are you surprised with this answer, Julian?
Well, I love quantum computing, so I think it's fascinating. I think it's the best answer, of course. But of course, yeah, it's quantum computing is still in a very early stage. It's extremely difficult to build a quantum computer. Well, we get into that later. It's still down the line, right? So neuromorphic computing might be much more easy to adopt in near term. So I'm a little bit surprised because we all talk about AI and how we can do this more efficient and on less energy and maybe on the edge. And these are applications we can already see in the near future. So yeah, I mean, it's a webinar about quantum technology, so I'm not surprised. But I do think that neuromorphic attention computing and also classical conventional accelerators also are very promising. But,
yeah, maybe it also has to do, with the way that we asked the question. So long term, probably I would agree. But then I'm talking about 10, 15 years from now. If you would ask me the same question, but then for the next 3 years, I would probably put my money on AI accelerators and neuromorphic computing because it's already there. Quantum computing, it's not there yet, right? So we have experimental machines that can provide, in a theoretical way, some idea of how a quantum computer works, but it's not there yet.
Yeah.
So I'm quite surprised. Of course, we should have asked the time scale at which this. Maybe it's good to shift gears and look a little bit about. Okay, so everybody is fascinated about quantum computing. We have high hopes for quantum computing. We see many companies investing lots and lots of money in it. But maybe we can go back to the fundamentals. So what's the fundamental difference when we look at quantum computing compared to conventional computing, Julian?
Yeah, excellent. So it's always a bit tricky to go in this topic because, I mean, who does, after all, know, how their own computer system works? Who knows about what logic gates are like and how many transistor works and how you have different chipsets, etc. I mean, usually you just use your computer and that's it. You program in some programming language, and you don't need to know about this basic level.
Mm-hmm.
But on the other hand, quantum computing is so fundamentally different that I think it's good to have a basic understanding of what the difference is, and in order to also identify what are possible use cases. So if you go to the next slide, I guess most people have heard something about this, but in classical computer we have bits. Eventually it's just currents going through your computer, going through transistors. We have some gates, logic gates, and we use some binary calculations, and in the end we build low-level languages, and then we build compilers and eventually operating systems using these bits. Very fundamentally, these two things, the very building block is different on a quantum computer. So a quantum computer uses quantum bits or qubits that are fundamentally different in the sense that they are not just a binary value, 1 or 0, but they are something in between. They are like a wave that is unset if it's 0 or 1. So maybe the most used example to explain this is you compare it with a coin. So if you flip a coin, I have a coin in my hand, and it flips in the air. It isn't decided if it will hit heads or tails, right? It can be either.
I have a coin.
Perfect. I'm not sure if you can see it.
It's a very
small. Perfect. If you flip it in the air, so it's head or tails, right? It's either. Like a classical computer.
Yeah, heads. It was heads.
Heads. So like a classical computer, it's either 5 volt or 0 volt. It's either heads or tails. It's one of the two values. Quantum computer is like being this coin flipped in the air, and it's undecided how it will eventually hit the table, and will be heads or tails. It's undecided yet. So it's a distribution of chances of how it will eventually turn out. And we can manipulate these chances. So it's not like it's 50-50, it will be heads or tails, but we can manipulate which value it will be. So I think that's the very core building difference. But the interesting thing is when you go to multiple qubits. So if we can go to the next slide. So if you can fly one coin and I flip it in the air, it's just a superposition, so it's either 0 or 1 or the values in between, but it's not so interesting, right? I mean, nothing really happens. But if you now flip 2 coins in the air, I'm not sure if you have another coin, Michiel, if you lost all of them.
I'm not that rich. I only have 1 coin.
So if you flip 2 coins and they hit the table, there are 4 different states that they can return into, right? With 2 coins, it can be heads.
0, 0, 0, 1, 1, 0, and 1, 1. Yeah.
Exactly. So all these states, they are simultaneously. But in a classical computer, it's just one state, right? They are on the table, and just one configuration at one point in time. So with 2 qubits, we have how many?
4 states.
Excellent. Yeah. So and with classical computer, we just have these 2 states. So I guess you feel it coming. If we go to multiple qubits, so say we flip 4 coins, we have a growing number of configurations that we can work with. So it turns out this scales exponentially. So with 4 states, I'm not going to ask you to name all the different configurations. It's 16 different options that you have. But with 4 states, we have 16 different states in which we can work with. So heads, tails, or etc. But on a classical computer, we still have only 4 different configurations. So this exponential scaling of 2 to the power number of qubits is the number of states that we can work with. And I think this is the incredible and fascinating point about technology, is that with only a very limited number of qubits, we have this extreme state space where we can work with. So if you have 10 qubits.
So what if I understand it correctly, so the quantum physics gives you the possibility to create, when you have 300 qubits, to have n to the 300 or 2 to the 300 possible states. But then with quantum, it makes it possible to have all those states simultaneously at the same time. And then by using smart algorithms from computer science, information science, you can actually leverage that specific quality where you don't have to go through the 2 to the 300s possibilities one by one, but you can go through them all at the same time, because all that data is available simultaneously.
Absolutely.
That's the big performance increase, right? If I understand you.
Yeah. So with only 300 qubits, so 2 to the power 300, which equals roughly 10 to the power 80, is equals to roughly the same amount of atoms that we have in our universe. So it's an extremely large space. And because it's scaling exponentially, if we add just one single qubit extra to our qubits, to our quantum computer, we again double the number of states that we can work with. So that's the main point. We have this extremely large space, and with smart algorithms, we can use these efficiently and manipulate these states simultaneously.
Yeah, so that's probably also why this where people are so considered about the potential of quantum computing when we look at asymmetric encryption, right? If you have a key space of 10 to the 1024 bits or something, then with conventional computing, it becomes not possible to go through one key after one key after one key, because it would take 1 million years. But with quantum computing, potentially you could very quickly find the key, because you can have all the possible answers at the same time in this. If you have 1024 qubits, you can have everything, all the values at the same time, right?
Yeah, so it's obviously a little bit more difficult than that, and there's a lot of difficulty in the details. But yes, that's the key points.
Okay, so before we move on, let's ask another Menti question, because Julian, you tried to explain a little bit what the fundamental differences between a bit and a qubit and what it would mean for compute power. Let's ask the simple question from the audience. Do you think you have thoroughly understood the nature of qubits? And the answers are very simple. Yes, I eat them for breakfast, or no, it's complicated. So let's see what the choices are of the audience.
Excellent. We have
So the number of people that say it's complicated is growing a little bit faster than the number of people that say yes, they have understood it thoroughly. Now, if I would answer the question, Julian, I would say no, I don't understand it thoroughly, it's complicated. What would you say? What would you say? What would your answer be?
I would say absolutely it's complicated. So I've studied theoretical physics for, 7 years, and still I don't really feel like I understand the basics in a naive, in an intuitive way. Mm-hmm. So I think there's this famous quote by one of the most famous physicists, Feynman, who said that if you think you understood quantum mechanics, there's so many things you've probably not understood it. And no one really understands quantum physics. So I think that's reassuring, because I mean, it's so tough that you probably don't understand the very fundamentals. But of course, it doesn't mean that.
So Julian, it's very good. So, but we both say no, we don't understand it thoroughly. It's complicated. We have 14 people that actually have answered yes, I eat qubits for breakfast. And so what I would like to do is to invite those 14 people to become part of our quantum community, because then they might be able to explain it to us, right?
Perfect.
Yeah. Okay, so Now, and there was already a question from the audience. I already saw that. Let's look a little bit beyond the technology, but then make a big shift and then talk about what would be the potential impact for quantum computing for companies like ours, because we are not in R&D, we are not developing quantum circuits or quantum chips or quantum computers. What should be the area where the opportunities lie for companies like Society or broader for Capgemini?
Yeah. So I think maybe you've been listening and you think, why do I need to know about these qubits and about how they interact? After all, I don't know anything about logic gates or transistors on my computer anyway. And I think that's a very valid question. As Capgemini, we're not an IBM. We don't develop quantum computers. Instead, we make applications for it. So the interesting thing is, because it's so fundamentally different, all kinds of software and technologies that build on quantum computers are also fundamentally different. So we can go to the next slide. If you think about classical computers and you think about transistors and logic gates, on the very lowest level, there's a server stack starting. So we have logic gates, and then we have some firmware, maybe some compilers. Then we program in different languages, right? We have a lot of people in Java or Python, maybe some frameworks on top of this, like Spring Framework, or well, you can go on. And you go up to with a server stack with different technologies, tools that you use. For quantum computing, of course, it's similar. But because the very basic building block is different, we will need different parts of this stack as well. So companies like IBM, they are working with making these systems, making machines that manipulate these qubits on the lowest level, and allowing tools for people like us to start programming on it. But the programming language aren't the same as classical programming languages, because it's a whole different kind of computer. So the interesting thing is that
IBM is providing this Qiskit environment, and Microsoft, I believe, they're providing something like Q Sharp, and Google, I don't know, but
exactly. Yeah. So it's not like if you want to get into quantum computing, you have to know how to manipulate the qubits themselves. You can also enter in a higher level. Qiskit, for example, has a framework in which you can use optimization problems. So you input the parameters for how you use a big optimization problem, and you don't really have to think about the lowest level anymore. But what you do have to do is think about what are the computational challenges in my problem. What is the why can't I solve this on a classical computer but on a quantum computer instead? What are the constraints that I use with my computer? How can I make this efficient so that it's suitable for a quantum computer? And these are questions that in many cases do not require you to be a physicist or a mathematician, but requires all kinds of different skills as well. For example, if you think about use case in finance, you need to know, well, one of the popular use cases is a portfolio optimization. You need to know what kind of input data do I have? How can I use this for my quantum computer? How can I build an application from this? All kinds of things that are interesting for us.
Yeah, so it would be, how do I, understanding the business issues at hand, whether you're talking with a bank or a logistics company or a pharmaceutical company, but then the other thing is, if I understand you correctly, is these quantum applications. It's about how do I define a problem as a quantum problem, and what part of the problem is actually a quantum problem and what's not, because
exactly.
A quantum computer doesn't work for everything, right? In some cases, it is superior than a classical computer, but in many cases, it's not. And you have to develop the wisdom to make the difference.
Yeah. So I think very broadly, we can say we need three kinds of roles. We need people that are able to provide workshops, that do maybe design thinking sessions to identify what is really the computational problem, How can we see where it fits within the company? How can we determine why it is so complicated? I think the second role that will be required and will be applicable for us is the quantum developers, you could say. So people that know how to speak the quantum language, how to pick the part of the problem that is really quantum and write it into such a language that you can run it on a quantum computer. And you don't have to know all the lowest level details, but enough so you can communicate with the quantum computers. And I think third is a role which is really low level, but it might not be applicable to us. So really knowing how to optimize these algorithms. You know, there are many research institutes that spend a lot of time on this, but we can instead collaborate with them and work with them to see how we can optimize our algorithms. So I think the first two are really something that we have a lot of capabilities for already.
Okay, so with this in mind, with these three areas of where we could provide value to our customers, maybe it's good to ask a timing question. And before I ask you the question, Julian, I will ask the question from the audience again. So it's another mentee question, and it's really about. I'm not looking at Society specifically, but more in general for all of Capgemini. When should we develop quantum computing services? And the answers are basically right now. Second one, maybe in 3 to 5 years from now. So we should start preparing, but it's not now. Then the other group is in the next decade, and then never. And what you see emerging, we already have 40 answers. Just over half of the people say right now. And then 35% of the people say in 3 to 5 years from now. And then 15% of people say in the next 10 years. So it's quite interesting that half of the people already say now. What would you say, Julian?
So it's a tough question, right? I mean, I would say now, but I think I would change the question from when should you start developing services to instead what should you develop at what point in time. So fault tolerant big quantum computers that are able to solve big optimization problems that might be even 10 years out the line. Investing in such machines is, for many companies, it's just extremely expensive thing to do, and it's very far down the line. But there are other investments that you could do and we can do that are would be very smart to do today. So one of the use cases for quantum technology is what you spoke about earlier, is to break most of current cryptography. So I think it would be very smart just to start identifying, what does this mean for my company? Is there a threat? Do I need to train people to be able to tackle this problem now or when the time comes? So I would definitely think that we, but also all of our clients, should really start to, maybe start with addressing like one quantum champion, one person that is an enthusiast, and see what it means for them. Because there are so many things down the line, and if you don't start developing services, you will be too late. Yeah,
so that's a clear, already a clear application of quantum computing. What you're saying is, although it will take probably maybe 10 years until we have this fault tolerant quantum computing with enough qubits to break RSA encryption. At the same time, there are already clients today that need to keep data secure for, let's say, the next 20 years or so, and they have to start worrying about this now and take precautions about this now. Just looking at the time, Julian, because before I will lose all sense of time, maybe it's good, and there's also some questions from the audience about business applications. So how is quantum computing being applied in business?
All right. So I think that's what we're here for, right? I mean, we want to make a business impact, and you want to see what are the use cases. So I think to summarize what quantum computers are good at is they are for big compute problems. So not necessarily for data crunching or for low energy AI systems, but instead they're for data for big compute problems, like really complex problems in optimization or other areas. So we can go to the next slide.
Where you have this combinatorial explosion, right? That's where they shine.
Exactly. So one example of this problem is what you see here on the right, many kinds of supply chain challenges. I guess this is quite a familiar problem, the traveling salesman problem, which is finding the quickest route between a number of locations. This seems very simple, right? Only with a limited amount of locations, we can draw the line and we can determine the fastest route. But if we go to multiple cities and we grow, there's this, what you said, this combinatorial explosion of number of states that we have. So with only a very limited number of sites, of space that we go to, we have this extremely large number of this combinatorial explosion, number of states that we have to solve for. So it's not completely sure if quantum computer will be the answer, but at least we know that classical computers will in many cases not be the answer. So there's good hope that we are able to use quantum computers for these kind of problems. Mm-hmm. But there are many more categories. So you can think about operations, resource allocation, maybe for planning the planes for KLM, for example, financial optimization. You said about, I talked about Airbus before, so fluid dynamics, a very computationally expensive computation, but also material science, all kinds of things in AI that are very compute resource expensive.
Quantum
and of course,
you mentioned, basically because chemics is a quantum problem, then quantum computer would work very well.
Yeah, absolutely. So we have, of course, do a lot of great things in quantum in chemistry, and we have a lot of computations that we use. And I think it's an area that is becoming much more and more computational. So we use more and more computer algorithms to solve for chemistry calculations. So, for example, for material science, creating medicine, stuff like that. But the problem is that this is such a difficult problem that we will never be able to solve it using classical systems. Not even if we use all the computer power in the world. But quantum computers, which use the fundamentals of quantum technology, are very well suited for this because they use the same. They are made from the same background. They are made from quantum technology while they try to solve quantum systems. So it's also a quote by Feynman, who said that for quantum systems, you need quantum computers to be able to solve them.
Okay, so there are a couple of questions about this. So the first thing is, are the algorithms that are required to solve these kinds of problems, are they already available?
So there are loads of algorithms available. If you go to quantumalgorithmzoo.com, I think, or if you Google it, there's a list of about 100 different quantum algorithms that are available. Mm-hmm. The problem is that we don't have the hardware ready. So we have we have some quantum computers, but they're in a very early stage. So we can run these algorithms, but we can run them only for toy problems. So if we talk about, for example, financial optimization, portfolio optimization, we can use these algorithms to solve for a portfolio of 10 or 20 items, which is nothing, right? I mean, we can just do a pen and paper.
Yeah. So the algorithms are there, but the real fault tolerant big quantum computers with thousands or millions of qubits, they are not there yet. But that doesn't mean that you can start experimenting right now.
Yeah.
Can you give an example quickly, Julian, looking at the time? Can you give an example of how a business is already applying quantum computing to what they do?
Yeah, excellent. So a quick point to what you said. So it's indeed for, we don't have the big fault tolerant quantum computers, but for many cases, we won't need these big fault-tolerant quantum computers. We can use smaller systems. So coming back to your question, give an example. So maybe we can go to the next slide. Michiel, what do you think is on this slide?
I think it's the mission to Mars that was just launched from the United Arab Emirates.
Yeah, well, I haven't seen that pictures, but this is not. No, instead it's a industrial process for nitrogenase, so we're building fertilizer. You can go to the next slide.
It's a fertilizer plant. It's a fertilizer plant. Okay.
Exactly. Yeah. So of course we build tons of fertilizer. It's a very heavy process, but it's a process that is using this Haber-Bosch process that is existing for about 100 years. It's been invented more than 100 years ago, and it's an extremely inefficient process. We use a lot of temperature, a lot of pressure, enabled to fix nitrogen. And actually, it uses so much gas. I think it uses about 2% of the world's gas consumption in order to develop fertilizer. On the other hand, though, what you see on the right is just this is water where bacteria are doing this process for free, right? They do it for room temperature. They do it 0 pressure or like room pressure. So it's unbelievable that we have all these big machines. We use a lot of gas, but we could just do it much easier. And the reason why we won't do it, just like these enzymes on the right, is that we just have no idea how they do it. And we have no idea how they do it because we can't look into the process. We can't simulate what they're doing because quantum chemistry is getting so difficult at this point that our current systems are lacking. Now, quantum computers, quantum algorithms are providing the hope that we can simulate and look into this process, and so we can replicate the way that enzymes are doing this process. So it's just one of the use cases for quantum chemistry, but it's a use case that is estimated to save maybe 2% of global energy consumption. And actually, though, you don't need too many qubits for this. Only with a few hundreds well-functioning qubits, you could do this. But you only have to be fault tolerant, so it's a bit more tricky. But yeah, it's just one example that is very promising.
And so, like you said, companies are already working on this, right?
Exactly. Yes.
Okay. So it's a real example. It's not a theoretical example. Listen, coming up towards the end of the presentation, I want to quickly go through a couple of questions that I'm receiving while we are having this discussion. And so, if you can just give me quick answers to those questions, then we can try to answer all the questions that are there. So, okay, so this is Sampath Kumar Yera. Hopefully, I pronounced the name correctly. I think quantum computing is more useful in scientific R&D applications at this stage, but do not find true industrial applications as of now. Do you agree?
So absolutely, there are no applications at this point which are in industrial scale. I agree that there's a lot of scientific interest for the foreseeable future. So quantum chemistry will be one of the early use cases. Yeah. So I agree, but I think it's moving much more towards optimization problems in the near future as well.
And can you give me a timeline for the near future?
So it's very tricky to say names, to say years.
Yeah, but is it like in the next 3 to 5 years, or is it a decade away?
So large-scale fault-tolerant quantum computing is definitely a decade away.
Yeah,
but
we don't need that, right? To have already.
We don't need it, exactly. We have a lot of innovation in using less qubits and also using very noisy qubits. So in the past year, we had this quantum supremacy event. Not sure if you guys had heard, but it's a point where a quantum computer did something that a classical computer would never be able to do. So in some point, they're already like just as powerful. But it was on something that was completely useless. They wasn't be able to use it for anything. But I think we will very soon hit a point where we can use it for something useful application. I think this will be in the next within the next 3 years. But it will be a niche problem, right? It will be used for something very specific. And then from there on, we can extend it to more useful and bigger applications.
Okay, Leon, you have to answer the questions in a shorter answer. Otherwise, we cannot make all the questions. So
Okay,
this is an interesting one from Virginia Mouville. Again, hopefully I pronounced the name correct. Is quantum computing energy efficient, or is it highly on energy consumption?
So these quantum computers, they are we have to operate them without having any environmentally noise, right? So if there's if you just have some temperature in there, everything gets destroyed. So they work in. Oh, sorry, I'm already feeling like I'm having more time for this question, so sorry for that. But they require a lot of cooling, so they're not very energy efficient. On the other hand, if you compare it with systems that would calculate millions of years, and with the quantum computer we can do it in seconds, it's limitlessly energy efficient. So it's a bit comparing apples and is that the Dutch expressions? With comparing different things.
Yeah, apples and pears. Yeah. Apples and pears. Okay.
Yeah, exactly.
So it's not that energy efficient because you have to cool the environment down to almost 0 Kelvin. But at the same time, if you're able to calculate something in an instant that would take thousands of years on a supercomputer elsewhere, then you might be more efficient than a conventional computer. Let me move to the next one. So this is about quantum computing and cybersecurity, right? There's a huge threat there, right?
Yeah.
But not today, but more in the not too distant future.
Okay. Yeah. So
I think you have answered then. So another one, are there other ways than qubit superposition of two states explored in order to do quantum computing? Quantum information vector with more superposition states, for example.
So there's a lot of different research in different type of architectures. We use different kind of qubits that are made for superconducting or trapped ion, but they are all qubits. So they use two states. And the reason why we use two states is because instead of like this vector, which you mentioned, is because it's much easier to have error correction, right? It's the same reason why we have binary computers, I guess, because if you have limited number of states, how can you do error correction? So as far as I know, it's not a big research field to have, quantum triplets or vector states. Most research is focused on different kinds of ways of realizing qubits.
So I have a couple more questions that are going into superposition and how do we fix the position of a qubit when it can change once we observe it and things like that. What I would propose is to have those very technical questions to answer them through after the session, through the Q&A session. But I have a last, which is quite an interesting question here. It's about quantum computing and COVID-19. So since there's so much already going on in research and R&D for finding a cure or finding a vaccine, what do you think about the relationship between quantum computing and COVID-19? Is it a solution? Could it be a solution, or could it be a solution to the next, maybe not for this virus, but the next one? What do you think?
So quantum computing is in full development. So I really hope that, for this COVID crisis, we won't be able to use quantum computers, because I really hope that the COVID crisis will be done in a couple of years. So no, for this crisis, it won't be much help, but for the next one, it might very well be. So there, of course, are many great people that do terrific work, so as doctors or researchers or epidemiologists, but also a growing number of computational scientists are working on tackling the crisis of COVID. So you can see this, for example, from the HPC HPC consortium led by IBM that does all kinds of computational problems relating to COVID. For example, they try to make vaccines, or they try to optimize the way we distribute the respiration devices. And all of these things are very computationally expensive. So for the next crisis, when we have quantum computers being more matured, this will be, it might provide numerous breakthroughs in tackling this problem by preventing it, by also to reduce the risk of the spreading and the outbreak. So actually, me and a colleague, Renate Wolters, have written a series of blogs about this topic. I actually understood it's being published today. So I think if we send the presentation, the slides, we can include this link. And in this blog series, we discuss these different fields of application where quantum computing might be fundamental to the way we tackle these kind of problems in the future.
Okay. So fascinating, and thank you very much, Julian, for answering all these questions and trying to explain a little bit about what the potentials of qubit of quantum computing. We saw 14 people that eat qubits for breakfast. Now somebody already made the comment that they might think that qubit is a breakfast cereal, so that's why they eat it for breakfast, but I don't know about that. So going forward, how could people actually start working on this? What's your advice if people got interested in this technology? Where should they start? Where should they find more information, or better, how could they start experimenting with this?
So there are many different programs online. So you have Qiskit from IBM, which is a very easy to enter set of tutorials, set of tools in which you can experiment. You have this from Microsoft as well, Quantum Q-Sharp, and it provides an easy access to not just look into the fundamentals of quantum computing, but also look in the application. If you really like that, of course, you can also always contact me. As you said, I mean, we really like to grow this community of enthusiasts that want to do experiments and want to have some point of views and explore what it means for Capgemini. So we have some things that we are working on. So different projects, different point of views or articles. So if you're interested, you can definitely email me as well.
Okay. So with that, I think so. People that are interested in becoming part of this quantum community within Capgemini, they could send me an email, and I will make sure that they get included in follow-up events that we're going to organize. We're already thinking about doing some training together with some of the partners like IBM or Microsoft. So just drop me an email, and I will include you in the list. I would suggest that if you want to stick around for a little bit more, I will open up the microphone to everybody so that you can ask your additional questions or have some comments or want to share some of your expectations. Please hang back, and I will open up all the microphones as we speak. And if you're not able, you have to move on. Then hopefully you enjoyed this first discussion on quantum computing. Thanks again, Julian, for sharing your vision and sharing the information.